The last video, I finished showing you schematically how we do physics simulation on a one-point particle. So given some initial condition x0 is 0, and we can compute the acceleration from the Newton's second law of motion, we can figure out what is the x and the velocity and the position at the next time, in some time in the future. And then we can propagate this over and over again, and this process is called time integration. So while at the previous video I showed you a very schematic intuition, in this video I'm going to show you in mathematical detail how this will work, and there's going to be a lot of math. I have a new tool here, so I hope this is going to work quite well. So it's very natural that if we do physics simulation, we have to use a subset, at least, of the laws of physics. And one law which we're going to use a lot is Newton's second law of motion, F equals ma. And of course, in animation, we are really interested in the position. We call it x. And this position, turns out that the derivative of the position with respect to time is the velocity, and the second derivative of the position with respect to time is acceleration. So or in other words, the derivative of the velocity with respect to time is acceleration. Excuse me. So we can actually substitute now in this equation, in Newton's second law of motion, we can substitute x for a. So the second derivative of x equals the inverse of the mass times the forces. Now, the previous example I showed you was actually using one-point particle in one dimension. Of course, this is never happened in practice. In practice, we work in 3 dimensions, and an object is made out of many points, so we say endpoints. So then the position x, the position of my object, is actually either a 3 by n matrix, so basically n points, and each point has an x, y, z. And if you use this notation, the mass, it's a matrix, an n by n matrix, diagonal matrix, and each entry of the diagonal, it tells us the mass of each point. And the forces, again, can be represented by a 3 by n matrix. So we have the forces which are applied at every point. Not every point have the same forces applied to them. So this is one way to essentially use this equation in matrix form. Another way is just to concatenate, to have one x to be one vector of 3 times n size, and but m still is going to be a matrix, and the forces we can also concatenate into one vector. So this is type of details that you have to worry about when you do your implementation of this, which you will have to do for your homework, assignment 3. But this is going to be more addressed in the lab. As it turns out, any physics simulation boils down to solve this equation 1. So basically, all we need to do if we implement rigid bodies, or if we implement fluids, or if we implement elastic objects, every time we have to solve this equation. So this seems to be very easy, but in fact, it's very difficult, because there's a lot of details on how to solve this equation. This is not a simple equation to solve, and then we have to see what kind of forces we have in each case. But we can appreciate that actually nearly everything in physics animation starts with this one equation. So let's look at this a little bit more in more detail. So x, it's the ultimate goal, the ultimate variable we need to solve. It is the position of my object, and again, an object can be represented by multiple points. So x it can be represented as a vector or a matrix, but it's not just one point; it's a collection of points packed into one variable x. And this is the goal. This is the variable we want to solve for. This x actually it's not a value, it is a function. X is a function of time. So x is the position of my object as a function of time. Moving on to the equation, so F is the number of forces that are applied to my object. This is actually, we assume they are known because we usually know the forces which are applied on our object, and this is the way we control the animation actually. So if we want the object to move in a certain way, all we can control is the forces. And actually, it's very interesting because this is going to be a challenge at the end. At the end of the physics-based simulation chapter, we'll see that in fact this is the biggest limitation of physics-based simulation, that if an art director for a movie or a game wants to have an animation in a certain way, the only way to, if you use physics-based animation, the only way to do that is by tweaking the forces, but it's sometimes a little bit unintuitive how much you have to change them to get a certain effect. So forces are also a function of, F is a function of time. The forces applied on my object can depend on time. Also, not every point in my object will have the same forces applied to it. M is very simple. It's assumed known. It's a function of that depends only on geometry. It's essentially the mass matrix. So now that we have figured out the variables in this equation, let's see what kind of equation is this. This is what we call the differential equation. Differential equation is an equation which solves for some functions, and the terms of the functions depend not only on the value of the functions but also on its derivatives. So in this case, we have the function, the second derivative of x with respect to the time equals something. So in as far as differential equation goes, we typically have two types of equations. One are ODEs, or ordinary differential equations, and the other ones are PDE, or partial differential equations. Difference are that the ordinary differential equations, they are functions of one variable, where partial differential equations, the terms that appear in the equation can be partial derivatives with respect to multiple variables. So our equation is actually an ordinary differential equation because our second derivative of the position, it is with respect to only one variable, which is time. Another way another nomenclature to classify differential equation is the order. Order means what kind of terms do we have. If we have first derivative, it's first order. If we have second derivatives, it's second order. If it's third derivatives, we have third order, etc. As you can see here, this is a second order differential equation, ordinary differential equation. Obviously, you can probably imagine that the lower order equations are easier to solve than the higher order. So already the fact that it's second order is not the best. The last point I want to make here is that the differential equation, ordinary differential equations are initial value problems, in the sense that you have to have some initial configuration. This makes sense if you remember from your high school calculus. When you integrate a function, you can integrate the function up to a constant, right? So if you add a constant to your function, you're going to have the same derivative. And so the only way we can uniquely solve a differential equation is if we have some additional information, some constraints. In the case of ODE, we typically have initial values. So we know, in our case, for example, it's easy. We know the position at the first time step and the velocity at the first time step, as it turns out. So these are the initial conditions for us. But for PDEs, for example, we have boundary conditions. So we need some sort of additional constraints to hold the solution in place. Otherwise, you can have infinitely many solutions, because when we do differential equations, by adding constants, those are removed when you differentiate. So for example, if x is a solution to this equation, x plus any constant is going to also be a solution to this equation. So this is why we need some ways to pin it down. So in this case, it's going to be the velocity and position at the beginning of my simulation. We call this usually t0. So we have seen the equation, we have looked at all the terms of the equation, we have understand what type of the equations do we have. We have a second order ordinary differential equation and an initial value problem. And now it's time to figure out how to solve it. Well, it's worth mentioning that actually solving differential equation is a field in itself, as they're very, the differential equations are very popular in physics. In fact, Newton, when he invented the differential calculus, this is the reason, because a lot of physics equations have to be expressed as derivatives of some of the functions, which makes them, differential equations. And there are lots of tools available, so we will explore some of them. But let's start with the previous observation that this is a second order ODE, and we would kind of prefer to be like first order at least. We have more tools to do that. So what can we do to simplify it? Then we're going to use a trick. Oh, to go back to the beginning. Okay. Okay. So we're going to use a trick. The trick is that we're going to package together into one variable the position and the velocity. So the reason why we have a second order differential equation is because we have the position, and then the derivative of the position is the velocity, and the derivative of the velocity is the acceleration, which is what we need in the equation. But we use the following trick. So our new variable, we have a change of variable, let's say. Our new variable y is going to be the concatenation, the vector between x and v. I'm using the word concatenation here is because, in fact, if you put it like x and v, it looks like it's two-dimensional, but it's not true. X, if it's in 3D, x is going to be in 3D, and you can have 3 times n values if you have n points in your object, and the same for v. So we abstract here this long vector as x and v. So this is our new variable y, which is the concatenation of x and v. So now we can change this equation 1 as it's shown here. So the first derivative of y, okay, well, is going to be equal to what? Well, the top part, which is x, I'm going to do it in blue. So the derivative of x with respect to t is going to be v, okay? And then the first derivative of v with respect to t is going to be the acceleration, which is essentially the second part, the right-hand side of the equation 1. So basically, by doing this little change of variable, which is just a mathematical trickery, we simplify the problem. So we moved from a second order to a first order. Oh, it should be ODE, not PD. I'll change it on the slides later. So it's going to be a first order PD, ODE. But did we, it seems like we gained something because we moved from second order to first order, but is this for free? No, it's not for free. We basically doubled our variables, right? So we start with a system. I mean, this equation 1, which I showed you before, we call it an equation, but as I mentioned before, it's really a system of equations because you can have in parallel many points on your object. So basically, we doubled our variables in our system of equations, but we pushed down the order, and this seems to be good, as you will see in a moment. So what's next? So next we are gonna visit a very old friend that I'm sure you saw before, which it proves to be very useful in such cases, the Taylor series. So Taylor series is essentially expressing a function around a point as an infinite sum of the derivative of that functions at that point. I'm not going to explain here the Taylor series, so I'm assuming you are familiar with it. I'm just going to refresh your memories. So if I have a function y, which is our function, I want to calculate the value of y at some t plus delta t. Remember that time integration is about moving forward in time. So we assume we know y at t, and we want to compute y at t plus delta t. So y of t plus delta t we can write using Taylor series, and it's basically an infinite sum of increasing derivatives. So basically, it's y of t plus the first derivative of t times delta t plus the second derivative of t times delta t squared divided by 2, and so on and so forth. Well, as you remember from your numerical analysis, if delta t is small, you notice that delta t appears here in increasing powers. So if delta t is very small, delta t to some power is going to be smaller and smaller, and is going to dominate eventually these terms. And so these terms essentially become smaller and smaller, which and they converge to 0 because of the delta t. So this means that this is an infinite sum, but the terms get smaller and smaller and smaller, so get more and more insignificant. So at some point we can cut and we can estimate our function. We cannot compute it, but we can estimate it using a finite summation. Okay. So this is what we're going to do here. So essentially, we will not compute the true function y because, well, we can't really. All we have to do is to estimate our function y at some discrete time steps in time. For computer animation, this is all we need really, because we want to render the model. So we're going to add something to the notation. So we're going to call tk the case time step. So it's t0 plus k times delta t. Delta t is the time step. Delta t is how much we advanced at every point. And tk is the case point in the future. And yk, it is our estimate of y of tk. Okay. So the game is the following. We want to estimate y. We don't know y. Y is the true solution of the differential equation, and we cannot usually solve exactly. We have to solve numerically. Numerical solution means you're going to estimate it at some points in time. And those points are yk. To give you an intuition of how this works, really it's basically like shown in this graph here. So the black curve is the y of t, which we want to compute. But we cannot compute exactly, so we estimate. And the way we estimate it is we compute the value at some discrete points in time, and basically from one point to the next we compute some sort of vector. So our yk plus 1 is going to be yk plus a step. We call this a step. So the game here is how to find this step. So our yk is the concatenation of xk vk, so the position at time tk and the velocity at time tk, and it's really y at t0 plus k times delta t. Is the estimate of y at t0 plus k times delta t. So the way we work is we're going to first look at the explicit schemes. The explicit schemes really, they truncate the infinite sum at some point. First order, they truncate it here. First order. Second order, truncate here. And not exactly so long and so forth, but more or less. So we are not taking into account everything after. The first method we're going to look at is called explicit Euler or forward Euler. It's the simplest possible explicit method, first order. So here I wrote again the equation. This is equation 2. If you remember, this is the differential equation we have to solve. The derivative of y equals the concatenation of v and m inverse f. So basically, if we use Taylor series expansion and we cut after the first order, after the first derivative, we have the equation yk plus 1 equals yk plus the derivative of yk times delta t. This is actually quite simple, right? So the position and velocity at the next time step is going to be the old time step plus the first derivative times delta t. So this is the simplest possible approximation we can have. And here here down here I show it how it goes. You can also look at the slides. It shows how it works when we put x and v together. Easy? I bet it is easy. It's very easy. This is pretty trivial to implement. If you had to implement all of this, it would have been wonderful. So as you can probably imagine, there are some issues, but it's easy. So essentially, how do we solve it is we start from t0 in steps of delta t, and we compute x and v using this formula. Note that in this equation 3 and also 4, because it's the same equation, everything on the left is unknown and to the right is known. So basically it's a substitution. There's nothing that you need to do. You just set the new yk plus 1 with something. So it's very, very simple. And of course, at t0, it's an initial value problem. At t0, we assume we have to know the position and velocity of our object. Let's give some intuition of the explicit Euler method using a graphical example. So here, the black curve is y of t, is the function we really are looking for. And we computed everything up to the point tk. So at this point tk, we know everything about, we estimated everything here, so we know yk and we know yk prime. So yk prime is the derivative, so it's a tangent to the curve. So essentially what we're doing here from the explicit Euler is we take the step in the direction of the derivative. So the yk plus 1 is going to be actually yk plus, we take a step in the direction of the derivative, which is actually the tangent on the curve. Well, as you can see here, if the steps are very small, you're probably fine, but once you have a larger step, like it's shown here, a bit exaggerated, there is quite a bit of error here, right? This is error, so this is not that small. So this is exactly the problem with the first method, is that it's very simple, but it has a lot of errors. So error can accumulate over time, and it's unstable. This is actually a very important point. The stability is critical when we do things like closed simulation. Stability is critical, and I will show you in a moment a video that shows you a bit what do we mean by that. So, but before we go to the video, essentially, error and stability, if we don't use super small time steps, and again, if we use very small time step, then it's a bit inefficient because we have to repeat a lot over and over and over again. And also, the problem is that we don't know how small the steps can be. So there is nothing that can tell us for this experiment, for this simulation, we need to use a smaller one, or we have to use a smaller one at the beginning, and then we can do bigger ones. So it's very difficult to determine how big or how small these time steps are as a function of your object or your simulation. So it's a bit of a game. So for movie production, it's okay because you do the simulation. If it blows up, you can redo it. But in a game, it's much more tricky. So this is where things get interesting. I want to show you now a video to explain what I mean. So this is an example. So this is the explicit Euler technique I showed you before. And this is what happens. This is a very simple implementation. Actually, I took from YouTube. You can see the link here. But it's essentially a simple closed simulation using springs, as it turns out, and it's held at 3 points, and it just hangs under its own gravity. So I don't think there's never even any wind or anything. So you see, this is what I mean by instability. So I play it again. So the beginning is sort of goes I would not say necessarily natural. It's too it seems too elastic, really. But at some point, the estimation goes way off, and everything is broken. So this can happen easily, and I think you will see that happening in your homework as well. So that being said, Euler, there's many uses for the explicit Euler. It's still used in practice in many places where it works fine. But if we want to improve, we have two orthogonal directions in how to improve it. One is we can improve the order. So somehow instead of cutting after the first derivative, cutting later. And this is going to provide a better approximation for our function. So we're going to look at some of the common higher order integration schemes are the Hune method, the midpoint method, which we're going to actually do in this course in a bit more detail. But you should know that the very common one is Runge-Kutta. It's a bit more complicated, and I'm not going to cover it in this course, partly because it is 100% sure covered in any numerical optimization course that covers partial differential or orderly differential equations, because it's a very good method, for a very accurate method, if a little bit slow. The other direction in which we can go is the backward implicit methods or backward methods. We're going to look in this course at implicit backward Euler. It doesn't improve so much the accuracy as the stability, and this is something which is very important for computer animation. So the backward Euler, even though it's a little bit more difficult to understand, it is used virtually in all class simulation and many other physics-based simulations. It's an industry standard because it's unstable. It's not necessarily more accurate because it's still first order, but as you have seen, if you saw the keynote from SCA, actually in graphics sometimes it's about how it looks. So if it looks good, we really don't want things exploding, so we want to be stable, and the implicit methods are unconditionally stable no matter how big your time step is, and this is very, very, very important. So I will start by showing first some of the higher order methods, the first two, and then we will spend some time to look at the implicit or backward Euler method. So before we go to the mathematical formulation in a moment, as it's often the case, I'd like to give you a little bit of intuition to understand what's happened behind the scenes. So when we do this time integration, the way we operate is we go in steps. So from k to k plus 1. So we don't care so much what is in between. So from tk, we take a step to tk plus 1. And the simplest way to do that we did with the explicit first order, was to go in the direction of the tangent. Okay? And if the time step is too big, you can have a pretty big error. Well, for the second order, the idea is to correct this step, right? So remember, when we have the Taylor series, so we have yk, and then we have delta t times y dot k, the first derivative, and this is this step here. But if we allow the third term, we have the second derivative delta t squared divided by 2. So this balances out, this has the ability to correct this step. And one way to think about correcting this step is, well, you can look at the derivative at the next time step and take the average of these two, as I can show you here. So instead of taking the step just y dot k, why not taking the step the average of these two? Well, what's the advantage of this? If the two derivatives are similar, then it doesn't matter. It's going to be the same as before, and it's going to be a good approximation. But if the derivatives are opposite, which is what happens in this case, and this is the worst case for the explicit first order, because the first derivative tells it to go a bit down, but then the curve goes a bit down, but then goes up. And because our time step is too big, we miss this inflection. So we're still keeping getting down. But once we get to tk plus 1 and we see, whoa, wait a minute, the derivative is in the other direction. If we take this average, whoa, no worries, I don't want to re-record this segment. It's just my son's rocket that we built today kind of fell apart. He's going to be upset in the morning, but if I take the average of these two derivatives, I can have a better step. So if you remember this would have been the error if I just have first order, and this is the error if I do the second order. So this is smaller, and it's typically smaller, the error. This is why the second order is more accurate. But there is a problem, right? There's a big problem, I would say. The big problem is how do we compute the derivative of k plus 1? We are trying to compute yk plus 1, so how come, we want to use derivatives? And this is where things get a bit interesting. So let's start with the details. So first, just for your to remember, this is y. This is the variable you are solving for, and this is equation 2, which essentially is the main equation that we have to solve. This is the ordinary differential equation that we have to solve, and the third row here is the Taylor series expansion cropped after the second derivative term. So if we allow one more term in our Taylor series, we have yk plus 1 equals yk plus the first derivative of yk times zeta t plus the second derivative times delta t squared divided by 2. Well, we have a problem because we do not know we do not know anything about this term, right? That is a problem. So how we solve it? Well, remember that the second derivative is the derivative of the first derivative. Why is this important? This is important because we can write, using the definition, we can express the second derivative using the definition of a derivative. If you remember, I wonder how many of you do, the derivative is actually a limit. So the second derivative of y with respect to t, if I express it as a first derivative with respect to the first derivative, it's essentially a limit as delta t goes to 0 of the first derivative of y with respect to t at t plus delta t minus the first derivative of y with respect to t divided by delta t. This is a limit. This is as delta t goes to 0. This is the definition of a derivative. All right, so how do we fit this limit in our case? Well, we already assume delta t is pretty small, so we're going to approximate it, the second derivative, using just delta t. So we're going to basically remove the limit from here. So now we combine equation 5 and 6. So when we put it together, we have yk plus 1 equals yk plus the first derivative of yk with respect to t times delta t plus the first derivative at k plus 1 minus the first derivative of k divided by 2. With a little bit of manipulation, you see that it's actually yk plus 1 equals yk plus the average of the derivatives at time k and time k plus 1, which matches exactly this picture here. But we have a problem, the same problem as before. We don't know the first derivative. Well, we don't know even yk plus 1, let alone the first derivative, because this is what we're trying to compute. So what do we do? Well, what do we do? Why not estimating it using the explicit Euler's method? So, oh, this is again on the other side. So why not estimate it using the explicit Euler method as before? But before I show you how this is done, we need to change the notations a little bit because we need to make it a bit more simple so that we can follow. And so here it's our original equation, y equals xv, and then the actual differential equation is here. We're going to simplify that. We're going to just say that our equation is the first derivative of y is written here. This is the new equation. This is the new equation we are solving. Then the first derivative of y with respect to t, it's f of t and y. So we're going to replace the right-hand side by just one name, f of t. Of course, f of t, f y, it is written here. and it's of course the same as before, like we didn't change anything really, right? So it's v of t, right? It's this one here and this one here, so there's nothing changed really. We just simplify the notation. We write it as an f of t and y. You will see why we do that. We do that because we're going to have to do a lot of manipulation, and it's a little bit easier if we have a more compact notation. And we put here in the equation 8 also the initial value, so we don't forget it. So that being said, we are solving now this, right? And just as a reminder, this is the first method we do, the explicit Euler becomes this. So this, you see how it's very nice and compact, right? It's very nice. This is how we like to have it in a more compact way. And now let's see how we do the actual second order method. So our new equation for the second explicit second order method is shown here, equation 7. So the new yk plus 1, it is yk plus, the step is the average between the derivative at k and derivative of k plus 1. As I mentioned earlier, derivative of k, it's simple to compute because we computed from the differential equation. So this is f of tkyk. But what do we do about yk plus 1? The derivative we don't have. So the answer is quite deceivingly simple. We can actually compute it from the first order estimate. So yk plus 1 we can compute using explicit Euler here, right? And then once we can compute y hat k plus 1, so hat is because this is the estimate of yk plus 1 with the first order, not our estimate of second order. And then we can just use the differential equation at time k plus 1, so we can estimate y dot k plus 1 by f of tk plus 1 and y hat k plus 1. Hat meaning was computed using the explicit Euler. And so if we put everything together, we have this result here. So xk plus 1 vk plus 1, it's xk vk plus delta t divided plus delta t times the average of the two time steps. The second one, it is actually the normal one, the yk dot, the one here. And the first one actually is the estimate of the derivative of the tk plus 1, which is computed from here. This method is also known as, I actually don't know how to pronounce his name, Hoon or Hone or Hune's method. And there's a slight variation. So there's a slight variation of this method called midpoint method, where instead of estimating yk plus 1 hat fully at k plus 1, we actually estimate it in the middle. So we take a smaller step to estimate the y hat k plus 1. So it's almost the same thing, some small adjustments. And this is called the midpoint method. Both midpoint and Hoon's method are more or less equivalent. And actually this small adjustment that we have made makes quite a bit different actually. So these are all the explicit methods that I'm gonna show in this course. So we're gonna move in the orthogonal direction to look at some implicit methods. You have seen this video before. So the explicit methods, especially the first order ones, are unstable if the time step is small, especially for games with like something more stable, and the implicit methods have very good stability. So we're going to dive into some details about that now. But before, let's look again at the intuitions that we have done so far. So the explicit Euler again, I'm repeating over and over again. I'm hoping that this part is going to stay. So we take a step from tk to tk plus 1 purely in the direction of the tangent. This can work well if the time step is small, but it doesn't work well if the time step is big and there's a lot of change in the derivatives, as it is the case in this specific example. The idea before with the second order was to say, okay, fine, so instead of taking the step just in the tangent direction from tk, let's combine the tangent direction and tk plus 1 in the hope that if they're both similar, then it doesn't matter. And if they are kind of in opposite direction, they will kind of cancel each other out, so we're going to get a better approximation. The challenge here was that, of course, we don't have this information, so we have to estimate it using first order, and this is what we did. But let's look at this problem in the more general sense. So we want to make the step using the first derivative of the point at tk plus something that, the derivative at the next, or averaging the derivative of the next point. But what if we just want to use the next point? So the idea between the idea of backward Euler or implicit Euler is maybe we shouldn't decide the direction of the steps based on the derivative at the current point. Why would we want that? Because the derivative can easily change in the future, so this is not the best idea. It seems to be a much better idea, at least from a stability point of view, if we estimate the yk such that the derivative, we estimate the yk plus 1 such that the derivative of yk plus 1, it is actually my step size. So this is why it's called backward Euler, because if I go to tk plus 1 and I take the derivative of tk plus 1, I get back to yk. So it's a reverse Euler. Instead of taking the derivative from the from the tk and go to tk plus 1, I try to find a yk plus 1 such that if I go backwards, the derivative is going to reach my point yk. This flip seems very unintuitive, and it took also me a long time to really understand, first, the method, and second, why is it better, and in which condition it is better, because as it is the case with all these methods, you can always engineer a case where one method is better than all others, right? So this is where we're trying to look at the most common scenarios and in practice, right? But this seems a good idea because what happens here is we're looking at stability. The instability happens when things go a lot out of place, like we go so far from our curve that we are starting to have very unpredictable behavior. And these implicit methods keep us on track. So it's saying, okay, at tk plus 1, I want to find a function at yk plus 1 such that the local derivative of this function points back towards me, right? So this basically ensures that I'm not going to escape too far from my target function y. I'm going to elaborate a little bit later again why this is so much better, implicit methods, or backward methods. So it's called backward because, it goes from, it basically tries to compute the derivative of the next point pointing towards me. But also it's called implicit because I don't know the derivative of this point, so I'm trying to find a point with the right derivative implicitly. And this is why it's called implicit. But both backward Euler or implicit Euler are correct. So the explicit Euler here in equation 10, the first line, it's what we had before. And actually the implicit Euler, it's very similar. So all we do is we change here f of tk plus 1 and y of k plus 1. So the explicit Euler was yk plus 1 equals yk plus f of tk yk times delta t. Remember, this f of tk yk encapsulated the right-hand side of the ordinary differential equation that we are solving. So the differential equation we are solving is the first derivative of y equals f of t and y. In the implicit Euler, we are saying, okay, yk plus 1 equals yk plus the derivative of the derivative of this unknown point in the future, right? So this is tricky to understand because we don't know this point. We want to find a point such that whatever point it is, the derivative points back to me. So it's an implicit method because we want to find this. We're going to find implicitly this point because we don't know it, right? So we want to find this point such that implicitly the tangent points back to us. So I already started to give you the intuition before, but basically I'm reinforcing it with emphasis on the stability. So the problem with the explicit Euler is that if the derivative changes a lot, my estimate can go too far away from the real curve, and then effectively escapes from the real curve. And this is what you saw in that example with the drape. The estimate was starting to be so far that it started to just bungle up. And the thing is, for the implicit Euler or backward Euler, this cannot happen because by construction, whatever point I look at, the derivative points back at me. So no matter what I do, I cannot go too far. Even if I have huge time steps, by construction, I cannot go too far from my real curve. And this is why it's called unconditionally stable. And it's very stable under large steps. But there's no free lunch. It turns out it's going to be much more difficult to compute because essentially we don't just have a substitution equation. If you remember all the explicit methods, we can work out the math that on the left-hand side we have the unknowns, and on the right-hand side we have the knowns. So all we have to do is to do a very simple computation. It may not have been simple because we have to kind of keep track of all the variables, but from a programmatically point of view, it's very efficient. Here, the right-hand side has unknowns. I mean, tk plus 1 is not unknown, but yk plus 1 is unknown. So f is a function of yk plus 1, which is unknown. And the problem is that this is an equation which is typically non-linear equation. So we have to have some sort of non-linear solver. Typically, the Newton-Raphson method, it's pretty efficient, and it's used to solve this equation quite well. We are close to the conclusion of this video, showing the various time integration techniques. They're very important. This is a very critical video for this module because the time integration is at the center of all our physics simulation. And so on this slide, I'm just writing it in a little bit more detail, the implicit Euler scheme. So the initial equation is simple. Yk plus 1 equals yk plus f of tk plus 1 and yk plus 1 times delta t. But now if we substitute correctly the f, you're going to have that xk plus 1 vk plus 1 equals xk vk, so the previous value, plus delta t times vk plus 1, because the derivative of x with respect to t is v, and we computed at time k plus 1. And then at the bottom we have m inverse times fk plus 1. So these are the forces at k plus 1, because the derivative of v is m inverse times f, which is the acceleration, and then we have to compute it at k plus 1. So you see we have v on the right hand side, but v is a very simple term here. It's a linear term. So that would not in itself cause any problems. You can just move it on the other side of the equation and you're fine. The challenging goes from here, that depending on what kind of simulation you have, the forces can depend on the velocity, and they do often. They can depend on position. And if they depend on velocity and position at the time k plus 1, tk plus 1, well, this means that they depend on, it's going to be these are unknown. And let's say one of the forces we're going to see is damping force, which depends on the velocity but depends linearly. But we're going to have common forces which are nonlinear, and in the velocity and position. And then if these forces are nonlinear in velocity and position, they will generate a nonlinear system in this variable. But the basic equation is pretty simple, I hope, to understand. And so this is a starting point for your implementation for assignment 2. And now we're going to do two-time integration examples, and I'm going to explain again more about the stability. So in the end, I decided to put the time integration example in a new video in itself. And so I want to clarify this image here. So this image here essentially shows the blue is the true y function. It's an example of a true y function. The red, and then the red and the orange or yellow are the approximations, implicit and explicit approximation at 1, 2, 3, 4, 5 points with a huge time step. So this example, I'm going to also do it in the next video. But I want to, because we have it on these slides here, I wanted to just show you the contrast between implicit and explicit if you have large time step. So blue is the actual function y. In this case, we assume we know it. And then red, it is the implicit Euler. So we computed so we started at 0, and then using implicit integration technique, we computed these points. Basically, the time step is 3, so it's a big time step, and we go from 0 to 12, so there are 4 points we computed, 5 points in total. What is interesting here is that, of course, you're going to have errors with these huge time steps, but with the implicit, the red curve, which is the estimated curve, the yk, if you will, follows roughly the shape of the curve. Yes, there are errors, no doubt, but it follows pretty nicely, I would say, for such a big time step. In contrast, the other one, this one, it's essentially the explicit Euler with the same time step. You cannot even see the points. The points are somewhere very down. So the first one is very much down, the second one is very much up, so it oscillates a lot. And this oscillation, again, is because if you take only the derivative at the start point and then the derivative changes suddenly, this is going to create this oscillating effect. So I could have shrunk this picture to show you the points, but it would not have been looked very good. So basically, the estimation of the explicit Euler it's way off chart. And this is a case where, for example, this is what happened in the video I show you with a drape that kind of starts to fly off in different directions. So this is exactly what happens. It's very unstable. Explicit is very unstable. Implicit, even though you have still errors, but for such huge time step, it follows the curve remarkably well. And in the next video, where I show you some example by hand, I'm going to also show you this example as well, but I wanted to also fit it here so that this video is self-contained. So now we move to the next video.